Hello, good day. My name is Dr. O.T. Afisi, and our topic today is Introduction to Logic. Many of you are not unfamiliar with the word logic. I'm sure that in your day-to-day interactions with people, you have heard of people use the word logic in many respects. Some people might say that your argument is illogical, or what you're saying is not logical, or you might have used it one way or the other in your discussions with people, how there's no logic or there's no sense in whatever they're saying. The word logic is not as simple as a lot of people feel. There are techniques, there are fundamental rules that one must understand in the concept of logic. However, logic itself is a basic tool of philosophy. There are many branches of philosophy in which logic is one of them. But logic is not strictly a branch. It is a tool that philosophy uses in its bid to drive home valid points or valid arguments. So when we talk about logic, we're talking about a technique of reasoning, or what we call a technique of critical thinking. And logic, as we have said, is a basic tool of philosophy. So if we say that logic is a technique of reasoning, or a basic a technique of critical thinking, then we're talking about the fact that philosophy itself, which is the mother of all disciplines, philosophy itself is about thinking. But you will agree with me that thinking is a fundamental feature of humanity. All human beings have the natural ability to think. And so we will say that invariably all human beings are philosophers, because philosophy is about thinking. However, even though all human beings have the natural ability to think, it is not all human beings that have the capacity for critical thinking. The capacity for critical thinking is deeper, much more entrenched than the ordinary manner or just the ability, the natural ability that we all have to think. The ability to think about what to eat at night, the ability to think about what to wear to school is just a natural feature. But it is not natural for everyone. It is not a natural ability for everyone who has the deep-seated capacity for critical thinking. The capacity for critical thinking is something that one has to develop to be able to get to the level at which people will recognize that what you have is a capacity for reasoning. The capacity for critical thinking is that which makes you stand above board. It is that which makes you stand out of the crowd. It is deeper. When all hopes are lost, when a certain problem has defied all technical solutions, it is the individual who has the capacity for critical thinking that is able to come up with ideas to be able to profile solutions to those kind of problems. I'm sure we have all seen the movie Superman, whether the animation or the real human Superman, where when somebody, for example, is falling from a 30-story building and everybody has started shouting, "Yay, Mugbeo," because no one has that ability to be able to rescue such an individual. What does Superman do? It comes from nowhere and rescues the day. And that is like the individual who has the capacity for critical thinking. And so, if we say that logic is that which is the capacity for critical thinking, then we're talking about logic as a basic tool or as a technique for reasoning. In this respect, we're using reasoning and critical thinking as a synonymous term. So the question then is, what is logic? The description that I've given is different from the definition. The description I've given is that which leads us to the definition that I'm going to give. The logic we're talking about is considered as the basic principles, the techniques, and procedures of reasoning for distinguishing between good and bad forms of arguments. And so, logic itself is a study which gives us the basic principles, the techniques, and procedures of reasoning. But what logic uses itself as a tool are arguments. And so when we talk about logic, you cannot study logic or use logic without some forms of arguments. Of course, when we talk about arguments, what mind is that of people quarreling. These people have arguments, there is this argument, you know. But in logic, what we call arguments are the tools. Arguments are the tools that logic uses to drive home its points. And the points that logic drives home has to do with whether a certain argument is valid or invalid. So in this respect, every argument has its own composition too. We have what we call premises in an argument. We also have what is called a conclusion in an argument. And so, what are premises? Premises are set of statements in any argument. They are set of statements in any argument. We're still going to see in the next section what premises are. And so, what we regard as premises are those set of sentences or set of propositions where that come before every argument. We can liken premises and the conclusion to an essay or a letter, a formal letter, for example. We all know that in writing a formal letter, the first thing we need to do is to start with an introduction. And thereafter we move on to the body of the work itself. In the body of the work, we might have as many paragraphs as possible, because each paragraph consists of a new point most of the time. And so the premises that we're talking about here begins with a premise 1, a premise 2, and that can also be likened, as I have said, to an introduction of a letter, of a formal letter, the body of the work by paragraph and paragraph and paragraph. And the last of the last of an essay is usually the conclusion, and we also have that in our argument. So in an argument, we have what we call premises and a conclusion. Premises can be we can have as many premises as possible, but the last one is usually the conclusion. All arguments are either valid or invalid, and of course, as we'll soon see, what makes an argument valid and what makes an argument invalid. What we call sentences in language, in logic, we usually call them propositions. I didn't say preposition, I said proposition. Proposition is the same thing as a sentence. If we say that a sentence is a group of words that make sense, it is the same thing as a proposition. Now, there are commonly two types of arguments. We have what is called a deductive argument, and we have what is called an inductive argument. In a deductive argument, we usually argue from a general situation to a particular instance. In a deductive argument, I take it again, we argue from a general situation to a particular instance. In an inductive argument, we argue from a particular instance to a general situation. We argue from a particular instance to a general situation. You will see in the example that I'm Okay, so look at the example of a deductive argument. We have on premise 1 there, we have all human beings are mortal. Premise 2, we have Socrates is a human being. And the last one there, which is the conclusion, we have therefore Socrates is mortal. I said in a deductive argument, we argue from general situations to particular instances. So look at the first premise there, premise 1. All human beings are mortal. All here stands for a general situation. Okay? All human beings are mortal. Then premise 2 goes down. Socrates is a human being. Therefore, Socrates is mortal. What you can see here is that the premises, the conclusion is derived from the premises. The conclusion is derived from the premises. Okay? And that is what makes this argument valid. Look at the example of an inductive argument. Premise 1, we have Socrates is wise. Premise 2, Socrates is a scholar. Conclusion, therefore all scholars are wise. Remember that I said that in an inductive argument, we argue from particular instances to general situations. Okay? So look at the example from premise 1. Socrates is wise. Look at that. It's particular. Premise 2, Socrates is a scholar. Therefore, all scholars are wise. So, it's very important for me to mention that deductive arguments are usually not based on probability. They are always true. They are always necessarily true because we will always see that it is difficult to criticize them. Okay? So, deductive arguments are either valid or invalid. But inductive arguments cannot be said to be valid or invalid. A deductive argument is valid if it is such that its premises are true, then its conclusion cannot be false. So look at the example. Remember the example that I mentioned. All human beings are mortal. Socrates is a human being. Therefore, Socrates is mortal. That argument is valid. Okay? And it is valid because its premises are true. And if its premises are true, then the conclusion cannot be false. However, in an inductive argument, there is what is called an inductive leap or a degree of probability. In the example that I gave, Socrates is wise, premise 1. Socrates is a scholar, premise 2. Therefore, all scholars are wise. If you look at that argument, if you say that Socrates is wise, the possibility that some other people who know Socrates may feel that Socrates is foolish or is stupid. So, if you look at premise 2, we say that Socrates is a scholar. Some people might believe that Socrates is not a scholar, is a dullard. So there is a degree of probability. And to now round off the argument to say that Socrates, all scholars are wise. I mean, that there's a difference between being scholarly and freedom. So there is an inductive leap in all inductive arguments because it involves some degree of probability. Now, we move to the next topic. Symbols of logical connectives. In logic, what we use are symbols. Okay? And the symbols are used as representation to discuss how arguments or propositions can form together. Okay? And the symbols are 5 in number. But before I talk about symbols, they are what we call variables. All the known alphabets are variables. Okay? All alphabets, 26 of them, A to Z, A, B, C, D, E, F, G, H to Z, are all variables. And so in most cases, we represent the variables, I will represent our propositions with variables, and the symbols that are used, that are also found in our propositions or arguments, we use the logical connectives to also represent them. There are 5 of them. The first one is called conjunction. The second one is called disjunction. The third one is called material implication. Some people call it conditional. The fourth one is called biconditional. Some people also call it equivalence. And the last one is called negation. Okay, so let's look at all these symbols of logical connectives one after the other with examples. As I said, there are 5 of them. So the first one is called conjunction. The word for conjunction is and. So whenever you find and in a proposition or in an argument, you know that it is to be represented with the symbol dot. The word for conjunction is and the symbol for it is dot. Alright? So if we find a word and in an argument, you know that it is the symbol dot that will be used to represent it. So let's take this example. Afisi came to school and Afisi taught logic today. Afisi came to school and Afisi taught logic today. Okay? As I mentioned earlier, what we use variables for is we use variables to represent propositions. Okay? If you look at the proposition that we have here, this is an example of a compound proposition. Alright? Because 2 propositions are joined together, so it becomes compound. If you look at it, it says Afisi came to school and Afisi taught logic today. We can actually break this proposition into 2. And if we break them into 2, each one will become a simple proposition. It can become Afisi came to school. That's one proposition. We'll represent that proposition with P, variable P. And the second proposition will be Afisi taught logic today. We'll represent that second proposition or a simple proposition with Q. Let me mention that all the variables are relevant. All the alphabets are relevant. But we, more often than not, we use P, Q, R, and S as variables for our examples, most times for our examples. So if you look at the example here, Afisi came to school, we represent that with P. Afisi taught logic today, we represent that with Q. And so if we have this example, this proposition, and you are asked to symbolize it, it will become P dot Q. Afisi came to school is P, and is dot. Afisi taught logic today is Q. Excuse me. So what we have there is P dot Q, and that is what we have done is to represent the word conjunction as part of the symbols. The second symbol of logical connective is called disjunction. The word for disjunction is or, and the symbol for it is ver. We call it V, but we call it ver. Alright? So if we have to, it means that whenever we find the word or in a sentence or in a proposition, we know that we have to represent it with the symbol V. Okay? So if we have this example, in every examination, the students will either pass or fail. In every examination, the students will either pass or fail. Alright? So what we have here, the first proposition before the symbol is represented with P. The symbol is ver, and the next proposition, which is just a single word, is Q. So what we have there is P ver Q. P ver Q. The third one is called material implication or conditional. The word for material implication is then, and the symbol for it is inverted C. I'm sure you can see it. The word for material implication is then, and the symbol for it is inverted C. And so, if, for example, we have this proposition, if Ada was tired yesterday, then she must have slept heavily yesterday. If Ada was tired yesterday, then she must have slept heavily yesterday. So if Ada was tired yesterday, we represent that with what variable? P. Good. Then is inverted C. She must have slept heavily yesterday is Q. So what we have there is P implies Q. P implies Q. Alright? So, of course, sometimes we call this in C the horseshoe symbol. The horseshoe symbol. Okay. The next one is called biconditional or equivalence. The word for biconditional is if and only if. The words for biconditional is if and only if, and the symbol for it is equivalence. I'm sure you all know the symbol for equals to, that is 2 lines. But this one is equivalence. You have 3 lines, so we call it equivalence. For example, Taiwo slept heavily yesterday. If and only if Taiwo was tired. Taiwo slept heavily yesterday if and only if Taiwo was tired. So Taiwo slept heavily yesterday is P. If and only if is equivalence, Taiwo was tired is Q. So what we have there is P equivalence Q. And the last one, the last of the symbols of logical connectives is called negation. The word for negation is not, and the symbol for it is a snake-like symbol. It's a snake-like, you know, it is snake-like. Now, the next topic is called truth table, and what we want to do with truth table is to see how we can use the 5 symbols of logical connectives that we have learned to how they can be expressed under truth table. Okay? And the first question you will ask yourself is, what is truth table? What truth table simply is for us to know whether a certain proposition is true or false. And so the description of truth table we have here is that it is a graphic representation of arguments to display all possible combination of truth values. And what are true values? For you to be able to determine if a proposition is true, then you must know if it is false. You won't know if a proposition is true if you don't know that something is false. So the true values that we have here are true and false. Those are the true values, T and F. Okay? So what we use truth table for is to determine the validity or invalidity of an argument using the truth table. Alright? And so let's go to the next one to see how we can use the symbols of logical connectives to check the conditions under which we can express the truth table. Good. Look at the first one, conjunction. Conjunction. The example we have in conjunction is the result of the example we have there is P dot Q, isn't it? Can you remember? P dot Q. Good. And so what we simply need to do in the first place, this, you can see that this is a table, but ordinarily if I had a blackboard or a marker board, what I would have done is to draw up a table in such a way that it will look like a cross. Okay, and there will be 2 sides. Of course, there you can see that in this table, inside the table, there are 2 sides. We have the side where we have P on the left hand side, and Q. Okay, so inside the left hand side of the table we have P, Q, and inside the right hand side of the table we have P dot Q. Okay, and so there are constant values that we need to learn in this table, and the values that we need to learn are the values of true and false. Look at the left hand side of the table, and inside the left hand side of the table you see under Q you have what we call true, false, true, false. Okay, and that is TF, TF. And what we simply need to do is for us to multiply each of these values under Q by 2 towards the left. And so if we multiply 2 times T, it will give us 2T, isn't it? It's like multiplying 2 times 1, it will give us 2. So 2 times T, the first T under Q, will give us 2T, and that is what we have written under P, TT. If we multiply 2 by F, it will give us FF, and that is what we have written next under PFF. And of course, the multiplication continues, but for lack of space, that's why we have just 4 lines here. And this PQ that we have on the left hand side are constant. They are unchanging, all right? The values of true, false at every point in time that you want to apply the truth table, okay, it is the same thing that you have to do. By the time we get to the next one, you see that the values are the same. So, and when you come under P, the next one, then you multiply what you have under Q by 2, gives you TT, under F, it gives you FF. But it's important for me to quickly mention that the variables that you have there are merely the variables that we have used as examples. There are times that you may have to use other variables like A and B instead of P and Q, or you use C and D, or you use E and F. So we can use any variable, all right? That's one. There could be other instances where you have more than 2 variables in truth table. And so what you need to do, I will just explain for lack of marker to describe. What you simply need to do is, if for example you had 3 variables, let's assume you had P, Q, and R, okay, what you simply need to do is to start your TF under R first, okay, and multiply by 2, it comes to under Q. I'm sure you are following me mentally. It comes under Q, and under Q you will have TTFF. Then the next one will now be P, because we have 3 variables here, P, Q, and R. So the third one will now be P, all right? And what you need to do here is to multiply the result under Q by 2. The result under Q will now be 2 times TT, gives you 4 T's. Then you write that 4 T's under P, TTTT. Then you multiply 2 times, multiply the 2 L's here by 2 as well. It gives you 4 F's. And that's the way it will go. Even if you had 4 variables, the same way you are going to be doing it. You multiply the result you have there by 2. 2 times 4 T's will give you 8 T's. And 2 times 4 F's will give you 8 F's. Alright, so now let's come back to this one, to conjunction. So the result of what we had in the example there is P dot Q, okay? And what we need to do is to use the values on the left hand side to be able to get the value on the right hand side. There are 2 variables, in the result there are 2 variables, and that's what they have written here, P, Q on the left hand side, and the result itself is what we have written on the right hand side, P dot Q. But as a rule, for us to be able to get the answer to this particular one, the you will see that the symbol here is a symbol of what? Conjunction. Good. And so the rule here states that the conjunction is true when both conjoints are true, but false in all other cases. In other words, the left hand side in this case is called the conjoint, all right, and the right hand side is called the conjunction. Okay, so the rule says the conjunction is true when both conjoints are true, but false in all other cases. So listen, the first one, let's look at it. It says under the conjoint we have TT. If we have TT, what will it give us? T. Good. If we have TF, it gives us F. If we have FT, it gives us F. If we have FF, it gives us F. Because the conjunction on the right hand side is true when both conjoints, the left hand side, are true, but false in all other cases. Good. Let's go. This one is called the disjunction. The disjunction, you can see that there are two sides as well. I mentioned earlier that the truth table is constant. Okay, the example that we gave for disjunction, if you look at it, also has two variables, and the two variables you have identified are the ones that you have written at the left hand side. Okay, the P and the Q, and the result of that example is what you have written on the right hand side, P over Q. All right, and I mentioned to you that the left hand side is constant. Is the Q here in this case, you write TF under it, you multiply by 2, it gives you TT under P, FF under P. All right, so this one too also has a rule. It says that the disjunction, rather, we're dealing with disjunction. The left hand side here is called the disjunct, the right hand side is called the disjunction. The rule says that the disjunction is true, which is the right hand side, when both disjuncts are true, or one of them is true, but false in all other cases. Now, let's look at the table. It says that the disjunction is true when both disjuncts are true. So when we have TT, it will be true. Or one of them is true. When we have TF, it will also be true. But false in all other cases. So whenever we have FF, it will be false. So let's take the example. TT will give us T, TF will give us T, FT will give us T, FF will give us F. Good. Let's go to the next one. Material implication or conditional. Material implication or conditional. Good. This one is a little different from the previous two that we have talked about. Although the same table applies. You first of all identify the number of variables. The number of variables on the left hand side that we have written is PQ, and the example that we gave is P implies Q. That's the result. Alright? The left hand side of this one, on the left hand side, the P is called the antecedent, okay, and the Q is called the consequent, and this other side is called the implication. The right hand side is called the implication, okay. And so the rule here says that the implication is false when the antecedent is true and the consequent is false. The implication is false when the antecedent is true and the consequent is false, but true in all other cases. So you need to pay attention to this very well. Okay, it is strictly not straightforward, but if you pay attention, you will get it. It says that the implication is false. Look at line 2. Okay, it says the implication is false when the antecedent is true. Look at line 2. The antecedent there is true, and the consequent is false. You can see that the consequent there is false. That's the only time it is false, but it is true in all other cases. So when we have true, true, what do we have? True, true, false, 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 true, true, false, false, true. It is true in all other cases. The implication is only false when the antecedent is true and the consequent is false. Good. The next one is called biconditional or equivalence. Biconditional or equivalence. This one, as I said earlier, the table is constant, especially the left hand side. We have two variables in the example, and the result is P equivalent Q. Alright, this one too is also called the P on the left hand side is also called the antecedent. The Q is also called the consequent. Alright, for us to be able to get the antecedent, the equivalent, the result, then we follow the rule. The biconditional is true when both antecedent and consequent are true, and when both antecedent and consequent are false, but false in all other cases. You need to pay attention to this one too. The biconditional is true. The biconditional here is called right hand side. When both PQ, that is antecedent and consequent, when both PQ are true, look at the first line. You can see that both PQ are true. Okay, that's when it is true. And when both PQ are false, look at the fourth line, the last line. When both PQ are false, alright, FF, that's when it is true. Then it becomes false in all other cases. Okay, so when we have true, true, what do we have? True. When we have true, false, what do we have? False. False, true, false. False, false, true. Good. Next one, and which is the last one. This one is called negation, and the table here is a little different from the previous four that we have talked about. This one has just one line. You know, if in negation, when you want to negate a particular proposition, if it is true, and you are asked to negate that proposition, then it becomes false, isn't it? Let's take, for example, a particular person you know tells lies a lot. Let's name the person Ade. Alright? And Ade ran into the room where you were and announced to you that it was raining outside. Ade came and said, it is raining. But because you know Ade very well, that Ade lies a lot, and you also observed that Ade's clothes are not wet, okay, Ade has told you that it is raining. Then you decided to go out to verify. Upon getting outside, you realized that it wasn't raining, that Ade was lying. So what you have done, what will you do when you come back? You simply tell Ade that it is not raining. Ade said it is raining, you said it is not raining. What you have done is to negate what Ade said. Okay? And that goes on both sides. So when you negate a true proposition, it becomes false. When you negate a false proposition, it becomes true. Okay, so let's take example here. Let's say the P here is it is raining, and the negation P here is it is not raining. So when Ade, look at what we have. When Ade tells you it is raining, we say it is T, it is true. But when you negate it, it becomes false. So it becomes, whatever you negate becomes false. If you negate a true proposition, it becomes false. When Ade tells you it is not raining, and you discover that it is raining, it means that you have negated it. What you have negated, what Ade said, becomes true. So, and it goes like that. True becomes false, false becomes true, and that is what negation is. Now, having learned the rules by which we can apply, we can use the symbols of logical connectives to apply to truth table. Now, it's important for you as students to undertake these exercises. What the rules, what the instruction here says is that we should use truth table method to determine the validity or invalidity of the following arguments. Okay, there are three exercises that I've given out. The first one here, premise 1 says P var Q, premise 2 says P, conclusion says therefore negation Q. Second exercise says P and Q, premise 2, Q implies P, conclusion therefore P or Q. Then the third exercise, which which looks more difficult, but it's not difficult if you know how to do it. Premise 1 here says P and Q in bracket is logically equivalent to P or R. Then premise 2, negation P implies P and Q, therefore Q or R. But what I'm going to do is that I'm going to solve the question 1 for you, so that you have 2 and 3 to do on your own. What I'll do is to solve question 1 and let you know how to determine whether the argument is valid or invalid. So as I've said, I'm going to solve the first, I'm going to give a solution to the first exercise. What we have here is P, premise 1, P over Q, premise 2, P, conclusion, therefore negation Q. The first step is for us to identify the number of variables. Of course, what the first step ordinarily should be that you draw up a table like a cross, all right, and you identify the number of variables that are present in the argument. And what are the number of variables that are present here? There are 2 of them. We have P, we have Q, and those are the variables that you are going to write on the left hand side of the table as I've already told you. And once you have written the variables at the left hand side of the table, we have P, we have Q, the constant values of true and false, T and F, that I've taught you, is what we start off with. You put your constant value of, or your values of true and false under Q as it is here. Then you multiply each of the value by 2. If you multiply value T by 2, it gives us TT, and we'll write that under P. Then we'll multiply value F by 2, it gives us FF. We write that under P. And so the next one under Q is just for us to fill up the space so that we can begin to solve the problem. The next step is for you to write down the propositions in the argument from premise 1. Premise 1 here. And for premise 1 here says P over Q. You write it down and give it its own column, as you have seen in the table here. So premise 1, P over Q. Premise 2, which is P, also has its own column, P. Then the conclusion, negation Q, also has its own column, negation Q, as you can see in the table. Now, the next step is for you to begin to solve the problem using the rules that you have already learned of the symbols of logical connectives when we apply them to truth table. The first one here for premise 1, P over Q. For the rule, you know that this is the rule of disjunction, okay? And the word for disjunction is or, and the symbol for it is ver. Now, what does the rule say? I'm sure you can still remember. The rule says that the disjunction is true when both disjuncts are true or one of them is true. Good. And so we'll have to go back to the variables to see. In this case, they will be our disjuncts. The rule says that the disjunction is true when both disjuncts are true or one of them is true. Now let us look at the variables, the values under P and PQ here. So it says, when we say true, true, what do we have? True. As you can see, we have written the T under P over Q. True, false will give us what? True, good. False, true will give us what? True, good. False, false will give us what? False. Because it is true when both disjuncts are true or one of them is true. The next one is for us to go to premise 2, which is P. It's standing alone. And since we're not going to apply any rule to it, what we simply need to do is to copy the things under P, all right, our true, true, false, false, and put them under P here as it is, as they are here, all right? And this is what we have done. The next step is for us to go to the conclusion, which is negation Q. Good. What we have here is negation Q, but under the variable Q here, what we have is true, false, true, false. And I've told you, for negation, if something is true, the solution to it or the reaction to it is that you have negated it, it becomes false. So everything under Q here, on the left hand side of the table, you negate them under Q here on the right hand side of the table. So true here will give us false, false here will give us true, true here will give us false, and false here will give us true. Good. So having completed the table, this is the first leg of it. The second leg, going by the instruction, is that we should find the validity or invalidity of the argument. To find the validity or invalidity of the argument, the instruction is simple, or the rule is simple. We will look for any of the row or rows in the argument that has true premises and a false conclusion. In this case, there are two premises and one conclusion. So we're looking for true, true, false. If we had three premises and one conclusion in this case, it means that we'll be looking for, in any row, we'll be looking for true, 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 false. Are you getting me? If the premises are 4 and one conclusion, we'll be looking for true, 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 false. Okay, but in this case, there are just two premises and one conclusion. So what we're looking for is any true premises and a false conclusion. We're looking for true, true, false. All right, now let's take it from premise 1 in the table. Let's look at premise 1 from P var Q to P to negation Q and see if we're able to get any of the rows here that will give us true premises and a false conclusion. Now, let's go back to it. Premise 1, line 1, true, true, false. Good. With this line 1 or row 1 that has given us true, true, false, it has made the entire argument invalid. All right? It has made the entire argument invalid. But it doesn't end there. You have to keep going to see any of the rows up till the last one to see if there is any of the other rows that makes the argument invalid. So line 2, let's go. True, 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 no. True, false, false, no. False, false, true, no. So it is row 1 that has made the argument invalid. So what you simply need to do is to write invalid row 1. Once you have written that, your job here is complete. Now, you are now expected to go to the other exercises that I've given you, exercise 2 and 3, exercises 2 and 3, and do on your own. If you have any issues or you have done it and you want to show me, you should get in touch. I wish you the best. Thank you.